Welcome back, students. We just completed, or almost completed, an example problem on hypothesis testing of two-sample inference associated to two independent proportions. I'm talking about this example problem, but I didn't say we completed. We almost completed. Why? Because this part is still a bit unclear. Let's come back to this problem. The null hypothesis, of course, is no difference. So basically, under the null hypothesis, first proportion and the second proportion are more or less the same. So no difference. But then again, what is the best point estimate of this pi value? Pi 1, pi 2, they are about the same. Is it 15 out of 150 or 6 out of 150? The best point estimate of pi 1 and pi 2, the common value of this proportion under the null hypothesis, is 21 out of 300, because put them all together and then they are total 15, they are total 21 defective, 15 plus 6, out of total 300. Make sense? So what we're looking for is the best point estimate of this pi 1 or pi 2 value. So that's P, and that's measured by 15 plus 6 over 150 plus 150. In a bit more general expression, this is going to be first sample size N1, and this is a second sample size N2. And this one here is going to be the first observation, M1, and that's M2. And in this particular case, it was 15 plus 6 over 150 plus 150. And that's approximately equal to 0.077%. Our textbook author used x1 and x2 in the numerator here. Let me expand the font a little bit. Oops, wrong key. But I was using x1 and x2 for the endpoints most of the time, so I didn't want to confuse you. So I use m1 and m2. And those are number of defectives in this case, or whatever the case if you're looking for the proportion, the numerator part. So that is the best point estimation. So under this, what is the SE? P1 minus P over N. That is the SE formula, isn't it? So if you do it this way, and calculate this thing, you get a drastically wrong number. And this is for one sample inference, not for two sample inference. Even under the null hypothesis, where the salesperson's new company versus competitor's company makes no difference. Even under that circumstance, under that null hypothesis, we have two samples. One sample of 150 and the other sample of 150. Here, I pulled everything together as one single sample. This is one sample. This is for one sample inference. This is wrong. So how do I make it right? Well, here is sample of 150. And here is another sample of 150. And these two are independent. And in this particular problem, we have 150 and 150. They do not have to be the same. You can have N1 and N2, which can be, say, 156 and 148. Anything will work. As far as this p-value is concerned, we reconcile them, right? Instead of using p1 and p2, just like we did for interval estimation for two-sample inference, we have to reconcile them into a single proportion, the best point estimate of the common value of pi1 and pi2 under the null hypothesis. So we have to add up the denominator, add up the numerator, and get new proportion there. No problem there. And then under this p, now that's a proportion that applies to both sample 1 and sample 2. So square root of p1 minus p over n, but we have different value n1, different value n2. And then we can apply the Pythagorean identity. If you do that, then what do you get? We have square root of this thing squared and then this thing squared. But then again, square root and square cancel each other, right? So this square gone, and this square root gone, this square gone, this square root gone. And now what do we have? We have p1 minus p common, and what's left is 1 over n1 plus 1 over n2. Oops. And that's how the new SE formula is coming into play. So, didn't make sense. Let's go back. Under the null hypothesis, you have to pull everything together and reconcile the two proportions. So the numerator is m1 plus m2, the denominator is n2 plus n1 plus n2. Pull them all together. There are total 300 phones in any manufacturers. And then out of that, there are total 21 defective out of all manufacturers. That is my common proportion. Under the null hypothesis, we have to have the same proportion, right? Same probability. So we use the same probability, p1 minus p, and then we have different sample sizes, n1 and n2. N1 and n2 happen to be the same in this particular case, but I can, of course, make these problems change a little bit. Instead of 150, change 156 versus 148. Okay, let's just do that. 156 and then 148. as good as any, and then calculate that thing. What do you have? 0.069, okay. That is my new proportion now, and that's not really of use, and that was just intermediate state. So this proportion is gonna be, let me just copy and paste one more time. And I don't need all this derivation anymore because I'm done with that. So this part is this, 1 minus that, and then I'm using 1 over 156, and then 1 over 148. If I adjust the problem just a little bit like this, you get a little bit different SC value. I didn't change a lot, you see. 156 versus 150, 148 versus 150. Didn't change a lot. Therefore, the proportion and the standard error didn't change a whole lot either. But in any case, from here you can complete the problem. You see, P1 is so 15 out of 156, and that is instead of 10%, 0.96%, 9.6% point. That is 6 out of 148. I have something like this. And the difference between the two is this minus that. And here we go. And then you can continue with your hypothesis testing with this. So 156, 148. I'm keeping 15 and 6 the same. Yeah, all right. Okay. The difference 0.556 something, and then critical value changed a little bit, but I didn't change a lot, so the conclusion didn't really change a lot either. 5% is a significance level, so still the same, rejects a null hypothesis and accept the alternative hypothesis. We ended up getting that. But of course, if I change the problem a little bit, change alpha value to something smaller, then this red region has to become smaller. So X value here, critical value, will retreat a little bit further or advance a little bit further depending upon how you're looking at. And conclusion may change, and indeed it did. If I change this to alpha value to 2%, what do we have? You can play with this kind of thing. So the conclusion, the hypothesis testing for two-sample inference is very different from just hypothesis testing of one-sample inference. we have to do a lot of adjustment. For interval estimation, there weren't too much actually. All we had to do was to use that new SC like this and take the difference. Then we could do the interval estimation for two sample inference for two independent proportions. Okay? If we have two dependent samples, then that was even simpler. Even same SC and everything will apply, so no problem there. But if you have two independent samples, then you have new SC, but otherwise everything stays the same. For hypothesis testing, on the other hand, you have to change a lot of things. You have to reconcile the proportions, and then you have to find that new SC, and so on and so forth. The structure of hypotheses also change accordingly, and so on and so forth. Okay, I'll leave the rest of the problem to you. What if you change alpha value to something different? I'm going to leave that to students. Okay, so much for section 2, and we're going to discuss sections 3 and 4 in separate videos.